I missed the introduction, but it's okay. So let's see what we can use these functional spaces for. I'll now discuss linear differential equations. And I will discuss this as a mapping because we have a mapping of this function x of t from one vector space to another vector space. And this is then the image function of this mapping. And we consider this equation here to be valid on an interval. Now, the image here is a continuous function. So this is a member of this set. The function or the solution to this equation here is, or I could say that the mapping is from a vector space Cn, and this means that these functions are n times differentiable. And if this differential equation is of order p, that is, it contains derivatives of, say, order p, then this is a mapping onto this class of function, and we consider these functions to be real functions. So this is the map. So imagine we have our domain, and this is Cn, and this is mapped onto Cn minus p, and in Cn minus p there's a subset C, or this is part of, this is part of C 0, and here you have the function q of t, so it's mapped into q of t. So it's q of t should actually also be in this subspace, which is the mapping of f. And generally, you have that the parameter is less than n, because if it was greater than n, then you would end up in a function that is not differentiable. Now, when is this differential equation here linear? It's linear when is linear when the map f of xt is linear. And this means that f should satisfy the linearity conditions. You have L1. If you add two solutions, to your equation, and you take the map of this, then this is equal to the sum of the maps f of x1t plus f of x2 of t. And also, you have that f of some constant times x is equal to a constant times f of xt. Now let's talk about the structure of the solution. Because since this map F here is linear, then you know that if you have this equation, then the solution is a particular solution plus the solution to the homogeneous system. So let me continue over here. The structure of the solution, the homogeneous equation is f of xt is equal to 0. And again, t is in this interval here. Now the solution, we call that the solution set, the solution set to the homogeneous equation, and this is equal to the kernel of the mapping F, as we learned last week. Now the complete solution is, and I write this as the solution set to the inhomogeneous equation, is the sum of a particular solution, I call it x0 of t, plus the complete solution to the homogeneous equation. And here we have that x0, or I'll just write, is a particular solution. This is very important because in this way you can build the solution to the differential equation. So this is more or less the basis for what I'm going to do now with a linear differential equation of first order. So let me write this down, how that looks. So I write here a first order linear differential equation. it looks like the derivative of the unknown function x of t plus some known function p of t times x of t is equal to q of t. And t is given in some interval of the real. I could write that explicitly, that I is a real interval. Now, the function p of t is a continuous function, and so is q of t. X of t, of course, because you have to take the derivative of the function, then x of t must be at least one time differentiable. And you can see here, if you take the derivative of x of t, you're sure that you have a continuous function here. The right-hand side is continuous, and the product of a continuous function and a differentiable function is a continuous function. So this should be okay. Now, let me look at the left-hand side of this equation, and I will consider this as a mapping. So I introduce now this left-hand side here. And I now claim that this is a linear map. So what should I do in order to show that it is linear? Use L1 and L2. Yeah. So let me do this. I take the sum of two functions x1 and x2 and put it into the to the formula for f. I get x1 of t plus x2 of t, and then the derivative of this plus so I take the derivative of a sum by summing the derivatives. And then I can multiply this function inside this parenthesis, or this bracket here. And then I can just rearrange the different terms here. I get x1 prime of t plus p of t times x1 of t plus then x plus p of t times like this. And you see, this is simply f of x1 of t, and this here is f of x2 of t. So my map f here, my transformation f here, satisfy the first linearity condition. And similarly, you can show that it satisfies the second linear condition. You have k times x of t. This is k times x of t plus like this. And here, when you differentiate a constant times a function, it will be equal to the constant times the derivative of the function. And then you can interchange the factors here, so you get k and then you can put k outside a parenthesis or a bracket, and you get k times f of x of t. So it also satisfies the second linear condition. So f is linear. So what I'm going to do now is then that I'm going to solve the homogeneous equation, because I need this solution. In order to build the full solution, I need a particular solution, and then I need a solution to the homogeneous equation. So let me start by solving solve the homogeneous equation. And this reads x of t plus x of t, or p of t times x of t equal to 0. What I'm going to do now is that I'm going to assume that x of t is different from 0. Yeah?
In the third step for the f of k times x of t, you just have to put k there.
Was it that?
Yeah.
Okay, thank you. Yeah. Thank you. So I now assume that x of t is different from 0. I'll return to the sign of x, and you can see if x is 0, it satisfies the equation. So it is a solution, but for now I assume that x is different from 0. And if it is different from 0, I can divide the equation by x of t, and then I get 1 times the derivative and you see here that this is actually the derivative of a combined function. So and it will be apparent if I write it in this way here. I take ln of the numerical value of x of t and take the derivative of this one, because when I shall take the derivative of this, then the derivative of, say, the outer function ln to the numerical value of x is 1 divided by x, but then x is a function of t, so I have to multiply by the inner derivative, which is x prime. And this is, there's an error here, because when I do this, I put pt on the other side, so there should be a minus sign here. Okay. But this is actually equivalent, this one, to this equation. If you take the derivative, you get 1 divided by x times x prime, and equal to that one, and then you can multiply by x, and you can take it, and you get this equation. So this is equivalent. But now it says that the derivative of this function here is equal to a known function of t. What is then the function itself? It is the indefinite integral of this function. So I integrate on both sides, so I get, on the left-hand side, I get ln to the numerical value of x, and then I get this indefinite integral. I could write plus some arbitrary constant. I call it k1 here. Now, this function, this indefinite integral of p of t, I call it capital P of t. This is the usual notation, and since it is difficult to see the difference between lowercase p's and uppercase p's, I put a small line at the bottom, and then plus k1. But it's not the natural logarithm of x that we want, it's x itself. So now we can apply the natural exponential function on both sides, and I get that the numerical value of x of t is equal to and then e to k1. So this is a solution to the homogeneous problem. We can write it in a nicer way, because this is a positive constant. Remember that the exponential function is always positive. But since I have the numerical value, I could have all positive constants and all negative constants here. But also, if you look at your equation here, x of t equal to 0 is a solution. So I can even have the constant 0. So I can write the full solution as k times e to minus, where k is an arbitrary real constant. So this is a complete solution to the homogeneous problem. And now we take a break for 10 minutes.